So in our previous lecture on 3D incremental plasticity, we had worked the flow rule basically down to a scalar hardening function times some function of the deviatoric stress, and we had assumed a von Mises yield function coupled with isotropic hardening. So I want to remind you of the equations that we talked about, that we had come up with from there, and then develop a method to compute that scalar hardening function. Okay, so let's begin by just recalling what those equations were. So let's say recall, we had sort of three basic equations. The first was the strain decomposition. Okay, so the strain decomposition was just that d epsilon ij was equal to d epsilon ij elastic plus d epsilon ij plastic. And just remember that when we do the additive decomposition, that tells you up front that we're talking about small strains, because those are the only types of strains that can be additively decomposed. Number two, we said that the elastic strain followed Hooke's law. So the elastic strain, or in this case the increment, could be represented as d epsilon ij elastic would be equal to 1 plus nu over Young's modulus E times d sigma ij minus nu over E d sigma kk delta ij. And then our third, and this is what we spent most of our time in the last lecture developing, was our plastic strain increment. So plastic strain. And I'll just remind you, this was specific to a von Mises yield function with isotropic hardening. Okay? Okay, so in that case, we could write d epsilon ij plastic is going to be equal to g, that's our scalar hardening function, times skl, right, where s is our deviatoric stress tensor, times dskl times sij, right? So this quantity, this skl, dskl, that's a scalar quantity, right, times another scalar quantity, this being our scalar hardening function. Okay, and if you think back to when we first developed it, we restricted it and said that it must be a function of potentially sigma and our internal variable state q, but not of d sigma. Okay, so we had already gone through those. So let's go ahead and just number these equations. There's equation 1, there's equation 2, and let's call this equation 3. So we want to ask the question, how do we compute g? What is this scalar hardening function? Well, and we want to maybe link it to what we can know about a material on the basis of things that we can easily measure. So something like maybe a uniaxial tension test. So let's go ahead and just consider that. So say consider a uniaxial tension test. Okay, so if we do that, let's just draw a picture of what our curve is going to look like. Here's our stress strain curve. So here's strain, here's stress, and I'm gonna go ahead and label this now. These are epsilon 1,1 and sigma 1,1 that we're measuring. So we initial linear increase, and then yielding, and then hardening. So at this location, that'd be our initial yield stress at sigma naught. The slope up until then is Young's modulus. If we pick some point on the yield curve, or at the point where yielding is happening, we would call that the E tan modulus, the tangent modulus, right? Okay, so what does the stress tensor look like in this case? Well, if we were to write it out, it's very simple. We're pulling on it with just sigma 1,1. That's a single component of the stress is non-zero, and that's what our stress tensor looks like. So from this stress tensor, we can go ahead and write the hydrostatic stress. Okay, hydrostatic stress which is, remember, is just 1/3 of the trace. So the trace here is just obviously sigma 1, 1. So sigma m for our mean hydrostatic stress is going to be equal to 1/3 times sigma 1, 1, looking at this up here. Okay, and that lets us also write the deviatoric stress. So deviatoric stress, if you remember, we could write S is going to be equal to sigma minus sigma m times I, right? That's how we define the deviatoric stress, which is going to wind up giving us sigma 1, 1 times the quantity 2/3, right? Because sigma 1, 1 minus 1/3 sigma 1 is 2/3. And then obviously negative 1/3 here. And negative 1/3. Okay, so let's go ahead and call this equation 4. We could similarly write the deviatoric stress increment. So the deviatoric stress increment is going to look very similar to that, right? We could just say then that d Sij is going to be equal to now d sigma 1, 1 times the same matrix, 2/3, 0, 0, 0, negative 1/3, 0, 0, 0, negative 1/3. Okay? We'll call that equation 5. Now let's go ahead and substitute these equations into equation 3. So let's go ahead and substitute 4 and 5 into 3. And when we do that, we have then d epsilon ij plastic is going to be equal to g. I'm just going to remind you it's a function of sigma and q. The next term was skl d skl. So that is going to give us, we're going to have this d sigma 1, 1 and the sigma 1, 1 pulled out. So sigma 1, 1 and d sigma 1, 1. And then we basically have the product of these quantities summed up. So this is going to give us 2/3 squared plus a minus 1/3 squared plus minus 1/3 squared. And then we have this quantity Sij. Okay? So let's go ahead and this gives me 4/9 plus 1/9 plus 1/9 is 6/9. Total is 2/3. So I am left with g function of sigma and q, possibly. Sigma 1, 1. Let me have it 2/3 here. Then d sigma 1, 1. And then Sij. Let's call that equation 6. Okay, but we talked about this already. What's our stress strain curve showing? It's really just showing the uniaxial stress and the uniaxial strain component. So we really are only showing from that curve epsilon 1, 1. So we can write then, so you can write the epsilon 1, 1 plastic now is going to be equal to g function of sigma and q times 2/3 sigma 1, 1 d sigma 1, 1. Now think about this. I just chose I and j to be 1, 1, so this now becomes S1, 1. If I go up here and look, S1, 1 is 2/3 times sigma 1, 1. So let's plug that in. Okay. Which now I can just take the product and combine the terms. This becomes g of sigma and q times now 4/9 sigma 1, 1 squared d sigma 1, 1. Okay, let's call that equation 7. So now what do? Well, we can use the strain decomposition on the left-hand side to write the plastic strain as the difference of the total strain minus the elastic strain. Okay, so now just say using the strain decomposition, which was equation 1, when we first wrote this down. On the left-hand side, right, we can write that this left-hand side looks like d epsilon 1,1 minus d epsilon 1,1 elastic, which is now going to be equal to g sigma and q times 4/9 sigma 1,1 squared d sigma 1,1. Let's call that equation 8. Okay, what do we know about d epsilon 1,1? Well, d epsilon 1,1 is d sigma 1,1 divided by the tangent modulus, E tan. And we also know that d epsilon 1,1 elastic is d sigma 1,1 divided by Young's modulus. So we can write this as the quantity 1 over E tan minus 1 over E times the quantity d sigma 1,1. So now you can see we can divide by d sigma 1,1. So dividing by d sigma 1,1, what we end up with is 1 over E tan minus 1 over E is equal to G times sigma Q, sorry, not times, as a function of sigma and Q, 4/9 sigma 1,1 squared. So this quantity here, we can do a little bit of work with. We can write it as E minus E tan divided by E times E tan. Okay? And we'd say that equals G times sigma and Q, not G times, sorry, G is a function of sigma and Q, 4/9 sigma 1,1 squared. Let's call that equation 9. Okay, so recall that we'd already defined this quantity back in our 1D plasticity discussion. This quantity, so let me just remind you, so recall, and I'll just remind you where, from our 1D plasticity, right, that we had defined the plastic modulus. So the plastic modulus is defined as H is going to be equal to E times E tan divided by E minus E tan. Okay, we call that equation 10. Where, how did we define this plastic modulus? We would say that D sigma bar is going to be equal to the plastic modulus times the increment in the effective plastic strain. Okay, and we also defined sigma bar. This is the yield surface boundary. In the case of isotropic hardening, it's equivalent to calling it the yield strength sigma y. Okay, so we can define that second equation as equation 11. Okay, so we can just substitute equation 10 into 9. Okay, so substitute 10 into 9, and all we're doing is using the definition of the plastic modulus to write that 1 over H is equal to, I'm going to just write G now. Well, maybe I'll just keep writing it as reminding you it's a function, or could be a function of stress in the internal variables, times 4/9 times sigma 1,1 squared. We'll call that equation 12. Okay? Now let me give you a little note here. We're talking about a material that is, we've assumed in this case that the material is isotropic and that our yield surface expands isotropically, that is without respect to where we are on the stress curve, really only as a matter of a radius in a particular, along a particular axis. So what that means is that via isotropy arguments, we could show that that G is really just a function of the internal variables, in this case, Q. So it can't depend on sigma. Okay, and that's again just due to isotropy arguments. If you're talking about anisotropic plasticity, then that would not be a valid assumption. Okay, so and then I also want to remind you that recall we had taken our internal variables Q just to be equal to J2 bar, right? J2 bar was our internal variable we were tracking. Okay? So what could we say? We can say, well, I can use equation 12. So solving equation 12 now for G gives the following, and we're going to make use of this note that says that G, now we're making it a function only of this J2 bar, which is an internal variable that we're going to track, is going to be equal to 9 over 4h times sigma 1 squared. Call that equation 13. Okay, one other note. What happens? What's going on during the strain hardening? Okay? Well, during strain hardening, which is what our loading curve is showing, during that time, sigma 1 is going to be equal to sigma bar, the outside of that yield surface, right? So this is the location of the yield surface. Okay, so let's call that equation 14. Okay, and we also can say something else about J2 and its relationship to sigma bar. So furthermore, note that we could write that J2 bar is going to be equal to 1/2 times sigma bar, the quantity squared, times the exact same thing when that we had to get us the 4/9, right, which is 2/3 squared plus a negative 1/3 squared plus a negative 1/3 squared, right, which ends up giving us 2/3 times 1/2, so it gives us 1/3 sigma bar squared. Call that equation 15. We can also we could write it in a little bit of a different way, and say that implies that also sigma bar squared is equal to 3 times J2 bar. Okay, those are equivalent statements. So now what you can see what I want to do, I'm going to just substitute equation 15 into equation 13. Okay? Well, via 14, right? So let's just say substitute 15 and 14 into 13. Right? And when we do that, we end up with that G is a function of J2 bar is equal to 9 over 4h times now this quantity 3 J2 bar, which is going to be equal to 3 over 4h J2 bar. Okay? Call that equation 16. Okay, a couple other things I want to note. What can we say about J2 bar? So where J2 bar begins at 1/3 sigma naught squared, right? The initial yield stress squared. All right, so let me just write that. That's the initial yield stress. Okay. What else can we say? And is governed by. Okay, so it is governed by, we can write that dj2 bar is going to be equal to 2/3 times sigma bar d sigma bar, right? And to see that, all I did was I took the differential of equation 15, okay, and then in terms of right here, this top equation, okay. So that's all we're doing. I already have some relationships for sigma bar, so this is 2/3. Sigma bar I know is going to be the square root of 3 times j2 bar. And I know that d sigma is related to the increment of the effective plastic strain via this term h, right? So h times d epsilon p bar. So I can end up getting the final quantity, which is 2 divided by the square root of 3 times j2 bar times h times d epsilon p, right? So that's how we evolve that quantity, that internal variable, with our effective plastic strain increment. I want to note that we just chose j2 bar for convenience of writing our yield function, okay? So we selected j2 bar as an internal variable, okay? But we could also have selected, we could have used sigma bar instead if we wanted, okay? But we could have used a sigma bar as an internal variable instead. Of course, that would have changed, potentially just changed some of the variables that we used when we defined our yield function if we'd done that, but it would still come out to be the same solution. Okay, so now what I want to do is kind of round this out and say I want to substitute equation 16 back into our flow rule, which, if you're taking notes along, was equation 3. And I could write the final solution as d epsilon ij plastic, the plastic strain increment, being given by g, which we said was 3 over 4 times h times j2 bar times skl dskl times sij, right? That's our general equation. Call that equation 18. And then also, just as a quick check, how about in the uniaxial case, we could write that d epsilon 1 plastic is equal to, here we go, 3 over 4h times j2 bar. And now this quantity up here becomes times 4/9 sigma 1 squared d sigma 1. So let's keep on carrying this out. My 4's cancel. My 9 and 3 can be reduced. So I'm left with sigma 1 squared divided by 3 times h times j2 bar times d sigma 1, which is going to be equal to, if you go back and then use the relationship between j2 bar and sigma bar, so this becomes sigma 1 squared divided by h times sigma bar, the quantity squared, times d sigma 1. And you can kind of do a gut check here and see, well, obviously on the load up, sigma 1 is tracking with sigma bar, so this actually becomes 1, and we're left with that the plastic strain increment in the 1 direction is equal to the d sigma 1 divided by the plastic modulus, which is in fact just the definition that we had originally given for the plastic modulus in the first place. We'll call that equation 19. So all of that works out well. The key feature in this, for this discussion, is that now we have a way to to account for plastic strain, as we can increment in any direction that we want, and any sort of full tensor, a fully populated tensor loading scenario.